Welcome back to Mechanical Engineering Made Simple.
Glad to be back.
So today we are heading out on a really unique deep dive mission.
We are.
We're going to explore the invisible choreography that basically keeps the entire modern world running. I'm talking about the massive unseen systems of material handling.
Oh, yeah. The silent partner of manufacturing.
Exactly. It's the lifeblood of literally every physical product you own, yet, it's a discipline that rarely gets the spotlight. At least not until a system completely breaks down and grinds production to an absolute halt.
Which happens more often than you'd think. And to truly understand the engineering rigor behind it, we aren't just going to read off a list of textbook definitions.
Right.
Instead, we're taking you on a story-driven walkthrough. We're going to drop you right into the middle of a common real-world engineering disaster.
I love this approach.
Yeah, picture this. You've got a sprawling, high-mix, discrete manufacturing plant. And this facility is currently suffering from plummeting overall equipment effectiveness. I mean, massive delays, damaged goods, sky-high operational costs.
A total nightmare scenario.
Absolutely. So our mission on this deep dive is to use core material handling principles to diagnose the chaos on that floor and systematically engineer a fix.
So imagine you are standing on the floor of this factory right now. It's an absolute crisis.
Total chaos.
You've got WIP work, in-process inventory just piling up in these random staging areas. Forklifts are completely deadlocked in the main aisles.
Horns honking, people yelling.
And then you look over and you've got these highly skilled CNC machinists leaving their actual stations, wasting valuable time manually carrying like 50-pound bins of raw materials clear across the facility.
It hurts to even picture it.
It's loud, it's chaotic, and management is pulling their hair out because lead times are slipping, but nobody seems to actually know where the real bottleneck is.
And here is where we see the classic rookie mistake.
The knee-jerk reaction.
Exactly. The common engineering reflex in a panic situation like this, especially, when management is breathing down your neck, is to throw capital expenditure at what is fundamentally a process problem.
Right. They think, well, we have a movement issue. Let's just buy a bunch of new equipment.
Yes. So they go out and procure a fleet of brand new forklifts.
Which is the worst thing you could do.
It really is. As any seasoned industrial engineer will tell you, buying equipment before fully mapping the system dynamics only treats the symptoms. You are essentially just adding more vehicles to a traffic jam.
You're just accelerating the chaos.
Precisely.
So as the engineer brought in to fix this mess, your proper first step is identifying and defining the true scope of the problem. You can't just look at the material handling equipment in isolation.
You have to look at the whole picture.
Right. You have to understand the products themselves, the intricate manufacturing processes, the specific takt times and production schedules.
And the actual three-dimensional layout of the facility.
Yes. You have to look at the factory as a living, breathing organism.
That's a great way to put it. And you can quickly categorize the operational failures on that floor if you break them down into the 5 fundamental aspects of material handling.
Let's run through those.
Every failure out there is a violation of at least one of these. First up, there's motion.
Okay.
This isn't just about moving things, it's about the kinematics of the floor. Moving things efficiently, safely, and with minimal energy. Right now, having people manually carry heavy boxes is a massive ergonomic liability.
And a terrible use of kinetic energy.
Absolutely.
Then there's time. This is your just-in-time delivery aspect. You need materials arriving at the workstation exactly when they are needed.
Not early, not late.
Right. Not 10 minutes early, creating a localized bottleneck that clogs up the operator's workspace, and definitely not 10 minutes late, leaving $1 million machine sitting idle, bleeding money.
The third aspect is place. Materials must be positioned correctly for use.
Point of use presentation.
Exactly. If an assembly worker has to turn around, walk 20 feet, and bend over to grab a component from a pallet on the floor for every single cycle, that is a severe failure of place.
It adds up so fast.
It does. Fourth is quantity. You have to deliver the correct volume to match the process demands, aligning your batch sizes with your single-piece flow goals.
And finally, space. This is about cubic utilization, not just square footage.
Oh, this is a huge one.
In our disaster factory, boxes and bins are spread out all over the floor in a single layer. They're paying for a 30-foot ceiling, but only using the bottom 4 feet. It's a complete waste of the facility's vertical volume.
Now that we've framed the scope of the disaster, we need to transition into diagnosing the root causes. We know the system is broken, but we need hard data to prove exactly where and why.
This is where we put on our lead investigator hats. We have to systematically collect data on this chaotic factory floor. You absolutely cannot just guess based on an afternoon of walking around with a clipboard.
No, you need systematic charting to capture the true flow dynamics.
Let's talk about the specific diagnostic tools used to uncover these root causes.
The foundational tool here is the flow process chart. This involves tracking a specific component or subassembly and tabulating every single step it takes, using standard American Society of Mechanical Engineers, or ASME symbols.
Right, the ASME symbol.
Yes, those symbols categorize every moment into operation, transportation, inspection, delay, and storage.
And when you actually chart this out for our broken factory, the data usually reveals something totally shocking.
This is always eye-opening.
You might track a widget and find it undergoes, say, 4 value-add operations, but it requires 12 transportations.
And a massive percentage of its life cycle falls under that ASME delay symbol.
Exactly. The actual value-add time might be 5 minutes, but it takes 3 days to get through the plant. It's just sitting in queues, waiting.
To visualize that inefficiency, we take that data and build a flow diagram. We superimpose those exact ASME symbols directly onto the floor plan of the facility.
So the abstract data becomes a tangible map.
Suddenly, you can physically see the chaotic spaghetti string paths the materials are taking, crossing back and forth over each other, creating massive cross-hauling waste.
But the flow diagram only shows us the current state. To figure out how to rearrange the plant, I'd bring in a from-to chart.
Right.
It's essentially a cross matrix that tracks the required number of physical moves or the flow intensity between different departments.
Yeah.
If the matrix shows that the milling department sends 500 loads a day to the grinding department, those two nodes need to be physically adjacent.
True, but adjacency isn't solely dictated by flow volume, which is why we pair the from-to chart with an activity relationship chart.
Right, because of the qualitative constraints.
Exactly. You might have a high flow volume between a heavy stamping press and a delicate coordinate measuring machine, or CMM.
Oh, you do not want those next to each other.
You absolutely cannot put a vibrating stamping press next to sensitive metrology equipment. The activity relationship chart maps those proximity restrictions.
All right, the data is in, and the bottlenecks are glaringly obvious. The factory is violating several of the core principles of the Material Handling Institute.
It's a textbook disaster.
They're moving single items haphazardly, wasting overhead space, and honestly, ignoring basic physics. So how do we actually start untangling this mess on the floor?
We systematically apply the core principles to engineer a new state. The first major intervention targets the floor clutter and the sheer number of trips being made. We apply the unit size principle.
Unitizing the chaos.
Right. Instead of having operators handle hundreds of individual cartons, we engineer unit loads.
And building a proper unit load is a science in itself. It's not just piling boxes on a standard wooden pallet and hoping for the best.
Definitely not.
You have to account for load stability and the center of gravity. If you stack cartons in a standard block pattern, where one column of boxes sits perfectly flushed on top of another, they lack lateral stability. They will tip over the second a forklift takes a corner too fast.
That's why we specify interlocking pinwheel patterns. The overlapping layers create structural integrity, much like laying bricks.
Makes total sense.
But even an interlocked load needs to be secured to survive transit dynamics. The entire unit load must be consolidated using automated stretch wrapping, which applies pre-stretched film to create a holding force or high-tension banding.
And once it's unitized, a single industrial truck can move what used to take an operator 50 individual trips.
Exactly. Now that we've consolidated the loads, let's look at the packing area. Currently, they have powered flat belts moving boxes a short distance to the loading dock.
Such a waste of power.
It's a perfect place to apply the gravity principle. Why incur the operational expenditure of electricity and the maintenance overhead of motors and drive belts when gravity is a constant?
Gravity is free.
It is. We pull out those powered belts and install gravity wheel and roller conveyors. By calculating the correct coefficient of friction and utilizing a slight downward declination angle, the cartons glide effortlessly to the dock.
It lowers the capex, eliminates a failure point, and costs nothing to run.
It's a huge win. With the packing area streamlined, we have to tackle the massive forklift traffic jams in the main arteries of the plant.
The trickiest part.
Human-driven vehicles are flexible, but for repetitive fixed-route transport runs, they introduce variability and safety risks. Here, we introduce the automation principle. We replace the manual lift trucks in those high-traffic, predictable loops with an automated guided vehicle system, or AGVS.
Now, AGVs sound great on paper. You see them silently gliding around modern facilities. But in a chaotic plant where someone might drop a pallet splinter or leave a tool cart in the aisle, don't those systems fail?
They used to.
Yeah, because I've seen older AGVs that rely on inductive loops embedded in the concrete just stop dead in their tracks if the floor gets damaged or blocked.
That was certainly true of older generations that required fixed physical guide paths. But modern AGVs and autonomous mobile robots, or AMRs, use advanced SLAM navigation.
Simultaneous localization and mapping.
Right. They utilize onboard LiDAR and vision systems to map their environment in real time. If an AMR encounters a tool cart left in the aisle, it doesn't just stop and trigger an alarm.
It just routes around it.
It calculates a dynamic path around the obstacle, ensuring continuous throughput while adhering to strict safety protocols. They never get fatigued, they maintain precise pacing, and they virtually eliminate the traffic bottlenecks.
Okay, we've optimized the horizontal movement, but we still have a massive cubic storage problem. We've got pallets taking up valuable manufacturing floor space.
Time for the space utilization principle.
Yes, the floor is for value-add manufacturing. The vertical airspace is for storage. To reclaim that square footage, we install an automated storage and retrieval system, or ASRS.
An ASRS completely transforms the physical footprint of a facility. We are talking about engineered steel rack structures that can easily reach 80 to 100 feet high, with incredibly narrow aisles.
It's an imposing sight.
It is. Down the center of each aisle, a computer-controlled storage and retrieval machine operates. It rides on a floor rail and utilizes a top guide channel to manage the extreme mass deflection that occurs at those heights.
The kinematics of those machines are wild.
They really are. The machine accelerates down the aisle while simultaneously hoisting the shuttle mechanism vertically. It calculates the optimal kinematic curve to reach a specific bin location on the 50th tier.
Smoothly decelerating to prevent load shifting.
Exactly, and automatically depositing or retrieving a multi-ton pallet with millimeter precision. It maximizes storage density and provides real-time inventory tracking.
But wait, an ASRS is great for massive pallet loads. What if this factory also handles thousands of unique, high-mix, low-volume components? Things like specialized fasteners, custom electronic relays, or raw plastic pellets for an injection molding wing.
A very common scenario.
You aren't putting loose plastic pellets on a pallet, and you don't need a 100-foot crane to grab a box of screws.
That's a critical distinction. Let's tackle the small, discrete parts first. For high-density, small-item storage, we scale down the technology and install a mini-load ASRS, or a horizontal carousel.
Oh, I love the carousels.
A horizontal carousel is essentially a continuous, motorized oval track of linked bins. Instead of a worker wasting time walking up and down static shelving aisles searching for a tiny part, which is a huge violation of our place-in-motion principles, the system operates on a goods-to-person paradigm.
The computer spins the carousel and presents the exact bin directly to the operator's picking station.
It's incredibly efficient. But before management signs off on millions of dollars in capital expenditure for 100-foot steel racks, laser-guided robots, and carousels, there is one non-negotiable final step.
You cannot just bolt this equipment to the floor and hope your from-toe charts were perfectly accurate.
Absolutely not. The crucial final step is computer simulation.
Building a digital twin.
Yes. As an engineer, you must build a dynamic, computerized model of the entire proposed layout. You feed the simulation your actual production schedules, your machine cycle times, and the kinematic profiles of your new AGVs and ASRS.
Because if you don't, you might just be shifting the bottleneck from one department to another.
Right. Precisely. The simulation allows you to run weeks of production in a matter of minutes. You can identify hidden system bottlenecks, test edge cases, and discover timing issues in the virtual world.
You catch the glitches before they're expensive hardware problems.
Exactly. For instance, the simulation might reveal that during a specific shift change, your entire fleet of AGVs will route themselves to the charging station simultaneously, totally crashing your throughput. You find and fix these logic errors in the code long before the millwrights start bolting metal to the floor.
So by applying these principles, unitizing the loads, leveraging gravity, implementing advanced automation, utilizing vertical space, and validating it all with a digital twin, we've taken a chaotic, failing factory and engineered a highly optimized, predictable system.
We've fundamentally changed the operating physics of the plant.
No, this walkthrough actually sets us up perfectly for our debrief. We like to take the most frequently searched online questions about material handling and ground the answers straight in the source text.
Sounds good. Let's do it.
FAQ number 1. Earlier I mentioned raw plastic pellets for the injection molding wing. The engineering solutions we just applied were all focused on discrete, countable items. So the question is, what is the difference between bulk and unit handling?
It's a distinction that often trips up systems design. Everything we've discussed so far, pallets, cartons, engine blocks, falls under unit handling. You are moving discrete entities.
Right.
Bulk handling deals with solids that are flowable. Think fine powders like wheat flour, pellets like soybeans, or lumpy coal. You move bulk using completely different gear.
Right, you can't stack wheat flour on a wooden pallet. Instead of an AGV, you might specify a screw conveyor, which is essentially a helical shaft in a pipe, or bucket elevators for vertical lifts.
Or pneumatic conveyors that suspend powders in a stream of air.
That leads right into FAQ number 2. Why do bulk materials get stuck inside storage silos? We've all seen massive industrial silos, but extracting material from them reliably is notoriously difficult.
It comes down to the design of the hopper, the sloped bottom of the bin, and the material's flowability. Ideally, you want mass flow, where all the material in the bin moves when the outlet opens.
But if you miscalculate, you don't get mass flow, you get funnel flow.
Exactly. In funnel flow, only a small vertical channel of material directly above the outlet moves, leaving dead zones clinging to the walls. To fix it, engineers use flow-assisting devices.
Like vibrating hoppers.
Vibrating hoppers or whirlpool devices to break up those cohesive bonds.
All right, final question, FAQ 3. When should a factory use a conveyor versus an industrial truck?
Conveyors are perfect when loads are uniform, routes do not vary, movement is continuous point to point, and the path is fixed.
They're relentless, but they lack flexibility.
Exactly. Industrial trucks like forklifts or AGVs are the go-to when you need flexible handling along variable or random flow paths.
It's incredible how much rigorous engineering goes into simply getting a part from point A to point B.
Before we wrap up, I want to leave you with a final thought to ponder. Consider the invisible choreography that surrounds you right now.
It's everywhere.
Almost every physical object you own was seamlessly passed from a gravity conveyor to a stretch wrapper to a laser-guided robotic vehicle and up into a 100-foot automated storage rack all without a single human hand touching it.
It's wild to think about.
Now, as artificial intelligence merges with these automated guided vehicles and automated retrieval systems, how long will it be before factories are no longer places where humans use machines, but rather giant, self-contained robots that simply operate themselves?
If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We love to hear from the folks who make this possible.